미국에겐 역사상 가장 치욕적인 날로 기록된 이날의 기억이 오늘 새벽 미일 정상회담에서 다시 소환됐습니다. 트럼프 대통령은 파견과 관련해 일본이 나서주길 기대한다고 말했고, 가까이시 총리는 원칙을...
Welcome to our lecture series on protection technology. These three Siemens Power Academy lectures are designed for those who want to expand their knowledge and understanding of relay protection for distribution and transmission grids. My name is Jackson da Silva, and I'm Senior Trainer from Protection System at Siemens Power Academy. In these lectures, I will have the honor to be the moderator. Today, we will focus on resistive faults in distance protection, mainly for professionals from distribution and transmission grids. We will record the webinar and make the recording and slides available to all participants. Please type your questions in the Q&A field. We will answer these during a dedicated Q&A session after the series. And now, let me hand over to our expert, Prof Lemmer. Siegfried, the stage is yours.
Hello and welcome to this session on resistive faults in distance protection. Unfortunately, this will not be an easy session, so we have to look at a couple of details which are necessary to get an understanding what is behind the setting rules you find in our manuals, the setting rules for the resistive reach of the zones in distance protection. And to illustrate the problem, I would like to start with a simulation. In this simulation, you see a line here from left to right. That's a part of a transmission system. That means these blue boxes are the remaining network behind the relays. This line is 100 kilometer, and you see we have some load on the line. And on both ends of a line, we have the distance relay. And down here on the left and right side, you see the first zone of these two distance relays. And in this simulation, we can simulate faults. And then we see what the distance relay will measure under these conditions. So let's simulate a fault at 80% of the line. So I put this slider here to 80%. And we can simulate a single phase to ground fault. And if I click that, you see here the fault is 80% of the line seen from the left relay. That means the setting here is 85%. That means this measured fault impedance is just inside the zone. And of course, the relay on the right side measures 20%. So the measured impedance is down here. We are talking about resistive faults. That means now I will add a fault resistance. In this case, a fault resistance of 5 ohm. And our first expectation would be that these two measured points would move to the right just by 5 ohms. So you see the setting of the zone in this case, in this example, is 20 ohms. And if we increase, we would expect, okay, we move to the right by 5 ohms, so we should still be inside the zone. So let's see what happens if we increase the fault resistance. We start moving. This is 5 ohms. And what happens is a little bit a surprise. On the left side, we move, but we move much more than 5 ohms. It's more or less 15 ohms or something like that. And we move up. We do not move horizontally. And in this case, already with 3 or 4 ohms, we move outside the zone and we wouldn't have a trip. And the other relay also moves. It's not exactly 5 ohms, and it's also not exactly horizontal, but it's not that extreme on that side. So you see, this looks a little bit confusing, and the intention of this session is to explain what effects come into the game and what do you have to consider if you want to calculate the setting of the resistive reach of a distance relay, taking into account resistive faults. So let's start the consideration with the easiest case. We consider a situation where we have infeed from one side only. That is not the typical situation in transmission, I know, but we have to go into the story step by step. So we start with the easiest situation, and that is infeed from one side only. That means in case of a short circuit on the line, we have no infeed from the other side. How does it look like then? We have this circuit. On the left side, we have the network behind the relay. Then we have our distance relay. Then we have the impedance of our piece of line between the relay and the fault. And then we have the impedance behind the fault. And if we want to simulate a three-phase fault, it looks like this. This would be a symmetrical three-phase fault. And in this case, this impedance down there is not relevant, because in case of a symmetrical three-phase fault, there is no current flowing from the start point to ground. This situation can be given into an equivalent diagram, into a very simple equivalent diagram. We just can look at the positive sequence system. It looks like that. So that is why we start with that, because we get the simplest equivalent circuit in this situation. So you see on the left side, again, the replica of the network behind the relay. Then you see the relay. And then you see the piece of line between relay and fault. You see in red the fault, and then the piece of line behind the relay, behind the fault. Our relay measures the two quantity, the voltage at the relay point and the current on the line. And the relay tries to calculate this piece of impedance between relay and the fault. Or we should say it more precisely, we want to calculate the reactance of this piece of line, because the reactance is an indication for the distance to the fault, and based on that we do the decision, is the fault on the line or not. So what do we have in this particular situation? We can set up the loop equation here in this loop. That is what the relay measures, and the voltage the relay sees is the voltage along this loop. That is the impedance of the piece of line multiplied by the current flowing there, plus the fault resistance multiplied by the current there. That is stated in the first line. And then if we rearrange that and then do that what the relay does, it wants to measure the impedance. That means it takes the voltage and divides it by the current. That is shown in the last line. And then the result of that is we get, as a result of our distance measurement, we get the impedance of the piece of line plus the fault resistance. And that is what we would have also expected in our simulation in the beginning. We measure the impedance of the piece of line, and then if we have a fault resistance, we just move to the right. And you see in this simple case, infeed from one end only and three-phase fault, the expectation would have been nice, would have been right. That means with a 5 ohm fault resistance, we would really move to the right by 5 ohm. That means in a symmetrical three-phase resistive fault with infeed from one side only, it's simple like that. But of course, the three-phase resistive fault is not the typical thing we have in networks. What we typically have are non-symmetrical faults, like phase-to-phase faults or phase-to-ground faults. And for that reason, we have to look at these faults and have to see how is in these cases the measurement influenced. And I would like to start with a phase-to-phase fault. So we start with the same arrangement again, but now put in a phase-to-phase fault. That means a resistive fault between two phases. in this case, the relay measures a face-to-face loop, and there the equivalent circuit looks a little bit different. You see here in the loop the relay measures, we have twice the impedance of the piece of line between the relay and the fault. That means the loop looks now a little bit different, and we have now to make up our mind how does the measurement react on that situation in case of this face-to-face loop measurement. And there we have to distinguish between the two distance algorithms we can activate in our relays. We have on one hand the RMD method, and on the other hand we have the so-called classical method we have been using for long times. That means you have to decide as a user which method you want to activate, and I would like to treat them here in the following slides in parallel so that you can see where do they lead to the same results and in which cases do we get different results in the measurement with these two algorithms. And that of course is important for the setting. That means you may need different setting depending on the algorithm you use. So that means we do the discussion on one hand for the RMD method, on the other hand for the classic method. So both use in this case more or less the same equivalent circuit. They split up the fault resistance into two parts and add them to the impedance of the piece of line, and the way they calculate the impedance differs, however. For the RMD method, we set up equations where we have the two unknowns. One is the percentage of the line where the fault is one unknown. That is of course what we want to know. And the other unknown is the fault resistance. And this percentage of the line up to the fault, that is called M. If you look into the description in the manual, that means one unknown quantity is this M, and the other one is the fault resistance. So the protection relay sets up the equation, solves the equation. We don't have to go into the details there. And the result is a value for M, which is an indication where the fault is. And that gives us this black arrow in the diagram. And then we add to that the fault resistance, and that is in this case half of the fault resistance. That means in a face-to-face fault with 5 ohms, we would measure the piece of line and then move to the right, not by 5 ohms, but only by 2.5 ohms. And we have to keep that in mind for the setting. For the classic method, the equations we solve are a bit different. The two unknowns are here not this M and the fault resistance. The two unknowns are the complete resistance of the loop and the reactance of the loop. That means the two unknowns are X and R. So we calculate the whole reactance of the loop divided by 2, and that is the vertical arrow, the reactance from relay to the fault, and we calculate the total resistance, also divided by 2, and that is this thing here, the sum of the resistance of the piece of line plus half the fault resistance. And that means both relays get the same result. They calculate this loop in a different way, but we end up with the same results. We have to keep in mind, whatever algorithm we use, in case of a face-to-face fault, we measure half the fault resistance. That was face-to-face fault without in-feed from the remote end. Now let's look at the face-to-ground fault. It looks like that. There we also have to think about what is the equivalent circuit of the phase to ground loop we measure in this case. And the important difference here is the impedance we see in the ground path. In a phase to ground loop, we see here this earth impedance. We often call it earth impedance. You should have in mind it's not something you can measure. It's an artificial quantity which can be calculated from the zero sequence data of the system. So what comes out of the algorithms there? Again here, RMD method and classic method in parallel. Let's start with the RMD method. It looks at this circuit, and here it does the same thing. We again start with this M, and then the algorithm again calculates the M, that is the percentage of the line where the fault is, plus the fault resistance, and gives that as a result. That means in this case, in case of a single phase to ground fault with 5 ohm fault resistance, we would really, using this method, we would really move to the right by 5 ohms. Again, that is relevant for the setting. For the classic method, the story looks a little bit different. The classic method also splits up the fault resistance here, and the classic method assumes that the resistance and the reactance both have a certain ratio between the upper path and the lower path in this diagram. And this ratio between reactance or resistance in upper part and lower part is a setting value. That is these zero sequence adaptation factors Kx and Kr you have to calculate and you have to set. That means the algorithm assumes whatever impedance we have there, they have always a fixed ratio, and that is why the fault resistance is split up in this strange way. That means if you add these two red resistances, you get as a result the total fault resistance RF. And the measurement, the result of the measurement of the algorithm, if we use the classic method, is the resistance we see in the upper branch. That means we get the impedance of the line to the fault plus this part of the fault resistance we see in the upper part, and that is the fault resistance divided by 1 plus Re over RL. That means in this case the classic method and the RMD method lead to different results in the measurement, and that means they also need different settings. And let's have a look at this a little bit more in the detail using the simulation. So in this simulation we have now the situation I discussed up to now. You see up here the infeed from the right side has been set to 0. That means the right side relay will not react because it doesn't see any current. And we are now going to simulate a phase to ground fault at 50% of the line. And if we give this a fault resistance of 20 ohms, you see with the RMD method we end up here. That means in case of a phase to ground fault, as we saw it on the last slide, the RMD method measures really the full fault resistance of 20 ohms in this case. We can take it back and now change the method to the classic method and see what happens if we increase the fault resistance again to 20 ohms. That's 21, that's 20. So you see here we do not move out by 20 ohms, we move out by 20 ohms divided by 1 plus Re divided by RL. That means we move out not that much, and that means the RMD method in this case requires a wider setting. We can do the same thing for face-to-face faults. So let's switch here to a face-to-face fault. Start with the RMD method again. Give a fault resistance of 20 ohms. Remember what should happen? In case of a face-to-face fault, we measure half the fault resistance. So we should end up at 10 ohms. Let's see whether that really works. Bring it to 20 ohms. That's here. And you see we are in the middle of the zone. That is nearly 10 ohms. It shows again face-to-face fault. We measure half the fault resistance. And there the classic method gets the same result. Also for the classic method, fault resistance of 20 ohms brings us at the same point at 10 ohms. So let's summarize the results we saw just in that simulation. This table summarizes the topics. I just show in the headline the line data we simulated here. We had a 400 kV line, 100 kilometer long. The total line reactance was 35 ohms. Resistance is 5 point something ohms. That leads to a typical line angle of 81 degrees. And what is also given here on the slide is the ratio RE divided by RL, which is relevant for our setting. And then we assumed the zone settings of roughly 30 ohms for the X reach of the zone and 20 ohms for the resistive reach. For the face-to-face faults, the RMD method measures, using this strange factor M, first of all the reactance of the piece of line to the fault, and then half the fault resistance, so we end up at that point. The classic method calculates a little bit the story a little bit in a different way, but basically the result is the same. So we also measure a resistance of 10 ohm, which is half the fault resistance. That means in these situations, face-to-face fault, both methods get the same result. We are still talking about in-feed from one side only and no pre-fault load. In case of a face-to-ground fault, we saw some differences. The RMD method measures the full fault resistance of 20 ohms, like shown here, whereas the classic method measures fault resistance divided by 1 plus RE divided by RL. That is a thing which is given in the data here, and in our case we had 12.6 ohm, so it measures a significantly lower value for the fault resistance, and that has to be considered with settings. That was the first part, considering in-feed from one side only. That is not the typical case in transmission, so we now have to consider what is going to happen if we have also in-feed from the other side. And also for this case, I would like to start with a three-phase fault, because there the equations are pretty simple. That is the diagram we already saw. That would be the equivalent circuit. Single-phase replica for a three-phase fault with a fault resistance with in-feed from one side only. Underneath you see the equations we already discussed. There we measure piece of line to the fault plus the fault resistance in case of a three-phase fault. And now what's going to happen if we have also in-feed from the other side? We have to add something to our equivalent circuit. That means we get an additional current called IB coming from the other side. That means in our fault resistance we have now current from both sides. that means we have an increased current in the fault resistance. And if we have an increased current, that means we have an increased voltage. And this increased voltage is seen by the left relay. That means the measurement, the distance measurement of the left relay is influenced now by the infeed from the other side because it increases the voltage across the fault resistance. If the fault resistance would be 0, there's no effect. But as soon as there is a significant fault resistance, this increased voltage will be seen by the relay and will influence our measurement. In this simple case, we can also set up the equations. We again do the loop equations, and the main difference is now, if we calculate this loop, we get here the voltage across the fault resistance is no longer only IR multiplied by RF, it's now IR plus IB multiplied by RF. And if we proceed in the same way as before, if we rearrange the equation, if we then divide the voltage by the current, what the relay does to do the measurement, then we see that as a result, it influences the measured resistance. We see we have this additional thing, IB divided by IA multiplied by RF. What does that mean? That means we see an increased fault resistance, and I add that here as a blue arrow. And the length of this blue arrow depends on the ratio IB divided by IA. That means, for instance, if we have the same current from both sides, this ratio IB divided by IA would be 1, and this would mean we would just measure double the resistance. And from that you can also see what is the critical case. The critical case is if a lot of current comes from the other side. That means if behind our relay we have a pretty weak infeed, and the other side has a strong infeed, that means this ratio IB divided by IA becomes high, and that means the blue arrow becomes longer, and that means we may have to take into account this longer arrow for the setting. We may have to increase our setting for the resistive reach. So that consideration has to be taken into account when we discuss the setting. And that's not all. You see, this ratio IB divided by IA is basically a complex ratio. So it could also be a complex number. And if this is a complex number, it brings us a certain angle deviation in there. Then the blue arrow could look like this or like this. And that means it also influences the reactance measurement. And that is a thing which is really disturbing. You see, in this case, we are, although the fault is inside the zone, we are moving up. So there is a risk that we leave the zone. And that is the effect we saw in the simulation in the very beginning of this video, where the impedance suddenly moved up. We will come to this thing later. We have to think about when does this ratio IB divided by IA, when does that become complex? And an easy consideration would be these two currents coming from both sides are in phase if the two driving voltages are in phase. And if you now consider the pre-fault state and the two voltages are in phase, that means you have no load flow. If you want to have load flow before the fault on the line, if you want to have load flow, the voltages on two sides must have a phase difference. And that means if these two voltages have a phase difference, and now you have a fault, then these two currents, IB divided by IA, have different phases, and if they have different phases, you have the situation that the blue arrow goes up or down. That means there is a relation between the pre-fault load and the question, where does this blue arrow move? That means we have to distinguish between situation without pre-fault load and with pre-fault load. And there is now one additional thing we have to consider. We have to look a bit closer at the type of fault we are dealing with. This consideration, these equations I show here, they are valid really for resistive faults. That means if we have a grounding resistance somewhere, or if some tree has fallen into a line, or if a conductor is falling to ground, faults which behave like a resistor. But in many cases, we have faults which are arc faults, especially if we have face-to-face faults somewhere on the tower, or if we have an overhead line, a face-to-ground fault. Also there we have typically an arc, and the arc fault has a different behavior. That means we also have to look at the behavior of an arc fault. Let's again look at this equivalent circuit here without infeed from the other side, and let's now assume that this fault is an arc fault. What does that mean? The arc has not a resistive characteristic, so the behavior of an arc is really a different thing. Of course, we have to make here some simplifications, and a simple approach is that you assume an arc is a fault where you have a constant voltage. That means the arc voltage depends on the geometry, on the length of the arc, and if you increase the current in the arc, the voltage doesn't change very much. Of course, it changes a bit, but it doesn't change very much. Doesn't change very much, and we assume the voltage remains constant. That means if you increase the current, that means the resistance you calculate decreases. And what does that mean now for the remote infeed? Imagine we have that situation with an arc fault, and now we make an infeed from the other side. We drive additional current through the fault, but now if this is an arc fault, the voltage will not increase like it would do with a resistive fault. The voltage will remain constant, and that means the relay on the left side doesn't realize that we have an infeed from the other side. The measurement is not influenced because the voltage across the arc remains constant even if we inject additional current. And that means we don't have to consider the blue arrow. And that's a good thing. That means for arc faults, we can more or less forget this story with these blue arrows. Summary of that, we again assume the two currents are in phase, then the voltage across the arc is not affected. The resistance decreases, but the measurement on the left side is not affected by that. And that is the good thing. We can just look at this thing, black impedance of the piece of line plus the red impedance. We can forget the blue impedance. If we have remote infeed, there is one thing we have to consider. Then IA and IB are not in phase, And that means if we inject current from the other side, the magnitude of the arc voltage remains the same, but the phase changes a bit. That means in this case, where IA and IB are not in phase, then the measurement is affected by the infeed from the other side, by this angle change of the arc voltage. That means in this case, it may influence the measurement. So you see, in this situation with remote infeed, it's important to distinguish between situation with pre-fault load and without pre-fault load. And for that reason, I would like to start looking into the story, first of all, without pre-fault load. That means if we have no pre-fault load, the two voltages are in phase, and that means also the two currents are in phase, and this ratio is a real value. And in the first step, I would like to discuss this ratio a little bit more in detail. For that reason, we look again at this simple circuit representing a three-phase situation. There the diagram is pretty simple, the equations are pretty simple. Remember, what we measure is the impedance of the piece of line plus the fault resistance plus this blue thing, IB over IA multiplied by the fault resistance. And if we have an example, we can make an example. We can, for instance, assume we have a ratio IB divided by IA of 3. That would mean if we have a 10 ohm fault resistance, the blue arrow has the length 30 ohms, 3 times 10 ohms. That means the resulting impedance would be, for a three-phase fault, 40 ohm. If we have phase-to-phase fault or phase-to-ground fault, we have to take into account again these things we discussed before. It can be half, or depending on the algorithm, in a single phase-to-ground fault, we have to divide it by 1 plus RE over RL. The thing I want to discuss here is this ratio IB divided by IA is not a constant thing. It depends, of course, on the situation in the network. Where do you have power stations? Where is the infeed? But it also depends on where is the fault on the line. If the fault is far away at the other end of near the other end of the line, that means you get more current from the other side. That means this ratio IB divided by IA depends also on the fault location on the line. And I would like to show this effect using a simulation again. So in this simulation, I will first of all show how it behaves without remote infeed. So we are using here the RMD method. I simulate a phase-to-ground fault with a fault resistance of 5 ohm. And if we move this fault along the line, so this measured point moves in parallel to the line characteristic. If we activate tracing, you can see it keeps pretty simple. This effect of the blue arrows is not there. We only have the red arrow. With the RMD method, we measure constantly 5 ohms. That means we have a line just parallel to the line characteristic in a distance of 5 ohms. So let's now activate the remote infeed. I bring it back to a pretty high value. So the first thing you see is we already move out a bit. That was the point we had with infeed from one side only. Now if we have infeed from the other side, we get this additional blue arrow. And the length of the blue arrow depends on the ratio between the currents from both sides. And now, if we move the fault along the line, what's going to happen? So you see we are no longer parallel. If we move along the line, the ratio between current from right side and current from left side increases. That means the length of the blue arrow becomes longer, and the further we are down the line, the bigger this distance becomes. And here you see we already move out of the first zone before we reach the end of the zone. And that is always an effect you have to take into mind. You have to calculate what is the ratio between the currents from both sides near the end of the line, because that is the critical thing. There the blue arrows are the longest. So this slide shows just 2 screenshots from the simulation we saw. You see, in this case, we had the same line. We had a fault resistance of 5 ohms. And there you see the different current ratios we had. The left diagram shows the situation for the left relay. When the left relay had a fault nearby, the current ratio was 1. And the reason, normally you would expect that the ratio is 1 on the middle of the line because it's symmetrical. In this case, I had a setting where the left side in feed was much lower than the right side in feed. So the left side had a little bit a weak in feed, the right side had a strong in feed. And that means even if the fault was directly in front of the relay, we had half of the current from one side and half of the current from the other side. If we now move the fault along the line, you see in the middle of the line we had roughly a ratio of 2. That means 1/3 of the current coming through the relay, 2/3 from the other side. And at the end of the line, in this case, we had a ratio of 4.4. That means the big majority of current came from the other side. The right diagram shows the same story for the relay on the right side, on the strong in-feed side, and you see there the effect is not that big. That means for the stronger in-feed side, the majority of current is always coming through the relay, and that means you have to be careful with this effect if you look at a relay which may have a weak in-feed behind it. So now we have to look a little bit more into the different fault types, because we still have to make up our mind what are we going to do with the situation that sometimes we have resistive faults, then we have to take into account the blue arrow, and sometimes we have arc fault, and then the blue arrow story is not so important. And let's look at the different fault types we have. The majority of faults are normally single phase to ground faults. And for single phase to ground fault, the typical case is we have an arc on the tower. That means that is an arc fault. But then the current flows into ground through the tower and also through the earth wire to other towers. And there we have a resistance. That means in case of a single phase to ground fault, we have both things. We have arc fault plus resistive fault. If we have phase-to-phase fault, we assume, also in our setting recommendations, that we just say phase-to-phase faults are typically arc faults. That means in the setting considerations there, we forget about the blue arrows. Phase-to-phase to ground faults, they need special treatments anyhow. I will show a few slides on phase to ground faults. So they require special attention. And three-phase faults normally do not need additional considerations, because if you make your settings correctly for single phase to ground faults and for phase to phase faults, then three-phase faults are normally also covered, because three-phase faults are on one hand pretty seldom, and on the other hand they normally don't have big fault resistances. So let's then look at a phase to ground fault with infeed from remote end. And that is the point where we have this combination of resistive fault and arc fault, and there we have to consider RMD method and classic method in parallel. That means for the RMD method we have this equivalent circuit. You remember that from one of the previous slides. The only change I made here is I split up the total fault resistive in an arc fault, that is what we have on the tower, plus the effective tower footing resistance. I will come to this strange term, effective tower footing resistance, a bit later. What are we going to measure there? Algorithm again solves the equation using this M. That brings us the complex impedance of the piece of line up to the fault. Then we measure the arc resistance. Then we measure the effective tower footing resistance. And this tower footing resistance is really a resistive fault. That means this part gets an additional blue arrow because we have also current from the other side. That means we have to add here the blue arrow. That means the red arc fault does not get a blue arrow. Only the resistive part, which is the effective tower footing resistance, that gets a blue arrow added, where the length depends on the ratio of the currents between the both ends. How does that look for the classic method? Remember, the classic method splits up the impedances using this ratio. That means we have to divide everything what we see there by 1 plus RE divided by RL, but the rest of the story remains the same. We also again measure the impedance of the piece of line plus the arc resistance divided by something plus the tower footing resistance divided by our factor plus the blue part divided by our factor. That means the result is similar to that what we saw before. In this case the two methods differ. The RMD method gets a higher value than the classic method. The classic method divides everything it measures by 1 plus RE divided by RL. And I would also like to summarize that in a table. We have here the same line with the same settings, and we assume that we have an IB divided by IA of 2 in this case, and we assume an arc voltage, an arc resistance of 12 ohms and a tower footing, effective tower footing resistance of 10 ohms. Then I will show here the RMD method and the classic method in parallel, and the upper part of the table is the phase to ground fault without remote infeed, and the lower part is the phase to ground fault with remote infeed. Without remote infeed, we assume a fault at 50%. We measure the total fault resistance, which is the arc resistance plus the effective tower footing resistance. 12 plus 3 is 15 ohms. The classic method, in case of a phase to ground fault, measures 15 ohms divided by 1 plus 0.593. That brings us to 9.4 ohms. If we now take this case with remote in-feed, same fault, but also in-feed from the other side with a factor of 2, that means twice the current is coming from the other side is a stronger in-feed, then we get this additional blue arrow. Before we had the 12 plus 3, 12 was the arc resistance, 3 was the tower footing resistance, and now the tower footing resistance get this additional blue arrow. The factor was 2, that means we have to add 2 times tower footing resistance, is 6 ohm, that means as a result we get 21 ohms. And that means we are already moving out of the zone. That means in this case, for the RMD method, we should increase the setting a bit. And for the classic method, we get the same value but divided by 1 plus RE divided by RL. That brings us to 13 ohms. In this case, we are inside. That is a consideration for phase-to-ground faults only. You may ask, what about the double phase faults, face-to-face faults? Remember the face-to-face faults, if we assume these are arc faults, then the story with the blue arrows is not relevant. That means there is no additional information coming into the game with remote in-feed. That means you can take the drawings from the previous chapter where we had a look at these cases without remote in-feed. So, and now there is one thing still missing. That is the question, what is going to happen if we have pre-fault load current? Pre-fault load current means voltage sources on different sides have different phase angles. And that means our two currents have different phase angles. The ratio is a complex value. And if we use the classic method, then we see something which can make trouble. I show here a case where the fault, you see here this black arrow, that is the impedance to the fault. You see the fault is just outside the zone. Then we have a fault resistance, and then we have this blue arrow coming in, and if the ratio IB divided by IA is complex, this thing is not horizontal, it can go down or it can go up. This is the case, it depends on whether we have load export or load import. In this case we have load export, that means the arrow goes down, and that means we have a fault outside, and with the fault resistance we suddenly move inside and we get a wrong trip, which is not nice. Also the opposite can happen. In this case we have a fault inside. Fault resistance brings us a little bit to the right, and then this blue part, in case of load import, moves up, and suddenly we are outside the characteristic. That means we have a missing trip. And that is a limitation you get with the classic method. You find there are a few workarounds around that, but that was one of the main motivations to introduce the RMD method, because the RMD method can compensate this effect. And that is really an important thing for the RMD method. That means the RMD method sets up equation, it needs some additional information, and it is also not possible to do that 100% exactly, but experience shows we can make a pretty good compensation and we can avoid a lot of these problems using the RMD method. And that is also the reason why we recommend the RMD method. We can now have a look at this story a bit more using again the simulation. So here in the simulation you see again our situation. We have in this case a weak infeed on the left side, a strong infeed on the right side, and what you see here is we have no pre-fault load. I simulate a fault at 80%. In this case, it is a face-to-face fault. And now if we increase the fault resistance, you see what's going to happen. Without pre-fault load flow, we move to the right. That means these blue arrows are horizontal because the ratio IB divided by AA is a real value because the voltages on both sides are in phase. Now let's assume we have a pre-fault load flow. So I set here a phase angle of 20 degrees. And that brings us to a load flow of 444 megawatt in this case. And now look what happens if we now increase the fault resistance. Sorry, I have the wrong method here with the classic method. With the classic method, you see the importing side moves up, the exporting side moves down. In this case, the exporting side, it's not that critical, but here we move up and we are already out of the characteristic with, you see here, already with 4 ohms, we leave the characteristic. In this case, we have a missing trip. And now we can repeat the same thing using the RMD method. If we now switch here our distance algorithm to the RMD method and then increase the fault resistance. So you see both relays have a horizontal thing. That means this tilting of the blue arrow is compensated by the use of the RMD method, and that is really one of the basic advantages of the RMD method. I would also like to show one additional thing with the classic method. In this case, we saw there is a risk that we can have a missing trip, but we can also consider a fault outside the zone, for instance at 90%. And now I change the direction of the load. Remember, if we have this direction of the load with import, we move up. And if I change the sign here of the load flow, put in a minus, so we have minus 20 degrees. Now you see the load flow is the other direction from left to right. And then if we increase the fault resistance, we move down. That means in this case, we have a risk of a wrong trip. And again, that can be avoided if you use the RMD method. Then we move horizontally. So we saw this effect of pre-fault load flow on the measurement of resistive faults. It's compensated if we have the RMD method. The classic method does not compensate that. And sometimes you find in the settings or in the manuals workarounds to avoid wrong trips with this classic method. And one approach is shown here. It can make sense to tilt the upper limit of the first zone a bit. And with tilting this zone, you can avoid the wrong trip. That means if you now have a fault outside the first zone, you get a fault resistance and then add the blue arrow, which has a certain slope. And if you tilt your upper limit, then you stay outside. That means by this you avoid a wrong trip. Of course, you have to do a little bit of calculation because you have to calculate what is the tilting angle of the blue arrow, and you have to set the angle of this upper limit of the first zone accordingly. Of course, this story has a disadvantage if you have the opposite situation. That means if you have load import, where the blue arrow goes upwards, then tilting the first zone makes the story even worse. That means it increases the risk of a missing trip. And if you increase the risk of a missing trip, you have always to think about what workaround can you do there. Normally, you will apply some teleprotection schemes in distance protection, which then can compensate that problem. But you must be aware that the different problems you may have, the different measurement issues, don't sum up in a way that even teleprotection does not work properly. So now we have gone through the different fault types. There's one fault type missing, and that is really a nice fault type. That is the face-to-face to ground fault. And that sometimes requires special attention. How can these things happen? Often it happens like this. You start with a face-to-ground fault somewhere on the tower. You have a flashover. Then you have this equivalent circuit with an arc fault plus the tower footing resistance. And then you may get a potential increase of the tower, and that may stimulate a fault on a second phase on the same tower. That means initiated by the first fault, you get an evolving fault there, and suddenly you have a face-to-face fault, and then the equivalent circuit looks like that. And I don't want to analyze the equivalent circuit here in detail, but what you can imagine is there you have a short circuit current coming from phase 1, flowing through an arc, and then through the tower footing resistance, and you have short circuit current from phase 2 also flowing through the tower footing resistance. That means in the tower footing resistance you have again a sum of two currents, and these two currents have a phase difference of 120 degrees because they are from two different phases, and this influences the measurement significantly. And we can also have a final look into my simulation looking at this particular case here. So in this simulation we go back to the easiest case. You see I have no infeed from the right side, no pre-fault load flow. We just look isolated at this topic of face-to-face to ground fault. I simulate here a fault at 50% of the line, and I have activated here face-to-face to ground faults. Of course, theoretically you need different settings for the arc fault and for the tower footing. In this simulation I only simulate resistive faults, so it's not exactly a good replica, but it shows the effect we have to take into account. So if the fault is at 50%, both relays will see the fault resistance at 50%, and both relays will in this case normally measure one face-to-face loop. Phase 1 and phase 2 are affected. No, in my simulation I have phase 2 and phase 3. So we will measure the affected face-to-face loop, and we will measure the two affected face-to-ground loops. And in this case, in all three loops we get the same result as long as we have no fault resistance. You see here in the table, 3 times we measure 17.5 ohms reactance to the fault. That is exactly of the middle of the line. That means here we have 3 dots at the same point. That means in all 3 loops, as long as we have no fault resistance, we get the same result. So what's now going to happen if we increase the fault resistance? It looks like that. And what's happening there? You see the right side doesn't see anything because there's no current flow, but on the left side you see without fault resistance all three loops get the same result, but if we increase the fault resistance, this effect that the tower footing resistance sees these two currents and that influences the measurement, that brings us to these results. That means the phase-to-phase loop moves more or less to the right. That means the phase-to-phase loop is not that much affected by the story. And one phase-to-ground loop moves up and one phase-to-ground loop moves down. And that is an effect which is not critical if we have a fault at 50%, then it doesn't really disturb us. But let's assume we have a fault at 90%. That means outside the first zone. What can happen then? Then this result suddenly moves inside the characteristic. That means we have a fault outside and we get a trip with that. And that is the leading phase here. The leading phase to ground loop in case of a phase to ground fault tends to have overreach. And that is the reason why you find a parameter block leading phase in the classic method. That means in many cases we can tell the classic method, if you see a phase to ground fault, please block the leading phase. Do not consider the leading phase because it tends to have overreach and it may generate wrong trips. In the RMD method, we have implemented a logic which is a little bit more sophisticated. That means in the RMD method, there is a special procedure which basically does the same thing, but only in cases where there is a risk that it disturbs. That means there you don't have to set this particular parameter. So here you see two screenshots from the simulation we just saw. On the left side we have the fault at 50%, and there you see how the measurements of the three involved phases move if we increase the fault resistance. The phase-to-phase loop just moves horizontally, and the leading phase-to-ground loop moves down, and that produces a risk of an overreach. The lagging phase-to-phase loop moves up. And on the right side we see the same story, but for a fault outside the zone where we should not trip, and we see that we can generate a wrong trip initiated by the measurement of the leading phase, which tends to overreach. And that is why in the classic method we offer a possibility to block the leading phase in case of a phase to ground fault. Let's state it here. There we have a parameter. The RMD method, as I said, has a particular logic to cover that, so this parameter is not necessary. So this parameter in the classic method is a little bit a critical thing, because you can imagine a few situations where this blocking of the leading phase can cause trouble, so it's not a thing which you can always do as a no-brainer. That was consideration of phase to ground faults. And now finally I would like, having all that what we discussed now in mind, I would like to show an example how we calculate the setting of the resistive reach of the first zone. And under what considerations do we have to do that? The first thing is we have in our relays different settings for phase-to-phase loop and for phase-to-ground loops. That means we have to calculate two different values for the resistive reach. And normally to calculate the settings for the reach of the face-to-face loops, we take as a base a face-to-face fault, and there we assume in overhead lines face-to-face faults tend to be arc faults in many cases. That means in our examples we ignore the blue part. That means for the calculation of the resistive reach for face-to-face loops, we only calculate the length of this red arrow and set the reach accordingly. Of course, if you have a system, let me say some distribution system, where you apply distance protection or a subtransmission where for any reason you also have resistive face-to-face faults because you often have branches flowing around or whatever, then you may have to do a different calculation at that point. And for the resistive reach of the face-to-ground loops, of course, we take face-to-ground faults. And there, for overhead lines, we can assume that this resistance consists of a fault of an arc, as discussed before, plus this effective tower grounding or tower footing resistance, RTF effective. So it looks like that. That means for the face-to-face loop, we take the arc voltage or the arc resistance, tower footing resistance, plus then the blue part belonging to the tower footing resistance. And the good thing here is normally the tower footing resistance is a bit smaller than the arc fault, and this blue arrow is only calculated on the base of the tower footing resistance and not on the base of both resistance. That helps us a little bit in making not too big settings. So that's one thing I just forgot. These considerations we will see now, they bring us to the minimum required setting to catch the assumed faults. However, it is always possible to increase the setting, to make the setting longer. You have to take into account other considerations to find out what is the highest possible setting. These calculations we will do in the next slides give us the minimum values. You also may have to think about what are the maximum values. That has something to do with load encroachment. You have to avoid that you move into the zone with heavy load. But one thing is also important, that is the last two lines here. If we get a result, then on one hand we have the reactive reach, which is 80 or 85% of the line reactance. That is one calculation. The other thing is now we calculate the resistive reach, and then we get the two results. And if these two values, the reactance of the first zone and the resistance of the first zone, if they are too different, if one setting is 1 ohm and the other setting is 20 ohm, then we would end up with a really extreme shape of the zone. And that can cause problems. We will have a separate session on these topics. And for that reason, we recommend that you keep this ratio between the R setting and the X setting in the range 0.3 up to 3. That means if your calculation ends up with something else, and we will see that soon, then you may have to adjust the R setting. So, but let's now come to how do we calculate the setting, starting with the face-to-face loops. We assume that these things are given. Nominal voltage, line length, that is what we all the time used in the simulation. What I have added here, I talked to somebody of the network planning department, and he told me when you have a fault on the line, you have a minimum short circuit current of 1400 and something amp for a face-to-face fault. And we also get from our network planning department the current ratio, which is not relevant for the face-to-face faults. And we also have the tower footing or tower grounding resistance. In this case, we assume it to 15 ohms. Of course, that is also a thing where you have to take an average value. You will not have separate measurements for every tower normally. That means you assume an average value. But of course, it can differ depending on the area where you are. If you are somewhere, if you are building a line somewhere in a desert or in a rocky mountainous area, you may have a higher tower grounding resistance than if you build your tower in plain land in wet with wet soil. That means the tower grounding resistance you normally would take an average value for the area where you are in. So let's start with face-to-face faults. Setting resistive reach for the face-to-face loop, we take face-to-face faults. There we assume that we have arc faults. That means we do not take into account these blue arrows I showed several times. The first thing we have to do, we have to calculate the arc resistance. And the arc resistance mainly depends on the current and the arc length. And the arc length depends on the voltage level and on the geometry, which is defined by the voltage level. And there is an approximation, says us, we can say we have 2500 volt per meter arc length. And for a 400 kV line, a rough estimation would be 7 meters arc length. So that is not only the length or the distance between conductor and the tower. Normally the arc has a little bit a shape, so it's a bit longer than that. So 7 meter is a good approximation for 400 kV system. And taking into account the minimum short circuit current network planning gave us, remember we need the minimum short circuit current here, not the maximum short circuit current, then we end up at 12 ohms. So what is now the setting? The setting calculates like this. Remember, for face-to-face faults, we have to divide the fault resistance by 2. That means in case of a 12 ohm fault resistance, arc fault resistance, both distance measurements will measure half the fault resistance. So we have to divide the 12 ohm. And of course, in protection, we are try to be always a bit on the safe side. That means we just add some 20% margin to that. That means in this case, the required minimum setting would be 7.2 ohms. And now the X setting comes from the length of the line, total reactance. If we set it to 80% of the line length, the full line had reactance of 35 ohms, 80% is 28 ohms. With that we would have this shape of zone 1. And here you see it's already getting a bit extreme. Now the ratio between the X setting and the R setting is 3.9. So it's a bit outside our recommended range, 0.3 up to 3. So we have to look into other parameters and see, can we extend the R setting? And for long overhead lines, we normally recommend to end up in a range of 0.5 to 1. That was the resistive reach for face-to-face loops. For face-to-ground loops, it becomes a little bit more complicated. We have here the same given values. We have to look, if we consider face-to-ground faults, we must have in mind they consist of an arc plus the effective tower grounding resistance. That means first of all we have to calculate these two values. The arc we assume the same as before, we take our 12 ohms, but what are we now going to do with this tower, effective tower grounding resistance? To understand what happens there, I take this picture that illustrates a bit the current flow. You see a few towers of an overhead line, and the middle tower has a phase to ground fault. And that means we have short circuit current coming from both sides through the phase conductor, and then at the fault location the current goes into the tower, and then one part of the current goes down in the tower through the grounding resistance of this tower, but another part of the current goes up through the earth wire to the neighboring towers. That means finally with this earth wire you get a parallel connection of the resistance of the affected tower in parallel with tower grounding resistances of the neighboring towers. And that is of course a complicated calculation. What is then the resulting resistance? And for that reason we use a pretty simple diagram you find in the manual as a support there in order to avoid complicated calculation. You find on the horizontal axis the average tower grounding resistance for one tower, and in this case we assume it is 15 ohms, and on this scale the 15 ohms is there. And then you go up to the lines, you see an orange line and a blue line. That depends a little bit on the type of earth wire you have there. And we take the orange curve, that means from the 15 ohms tower grounding resistance we go up to the orange curve, and then on the left we can read the effective tower grounding resistance, taking into account the parallel connection of the neighboring towers, and we end up here at something like 1.5 ohms. That means although one tower has a grounding resistance of 15 ohms, the thing we really have to take into account for the calculation is only 1.5 ohms. That means this earth wire, which distributes the current to different tower, really reduces us the grounding resistance, and that helps us to avoid very long settings. Arc resistance, we assume the same thing as before. Of course, theoretically it could also be different for phase to ground faults. And now when we calculate the settings, we have to distinguish between our two algorithms again, because have in mind for phase to ground fault the RMD method brings us different results in comparison to the classic method. That means also the settings must be different. For the RMD method we assume this. That means we also take the 20% margin. So we do a calculation, but we add 20% to be on the safe side. Then we have the arc resistance, which doesn't get the blue arrow. Below you see that is 12 ohms. And then we get this effective tower grounding resistance, and that has a red part with a 1 and a blue part. And in this case we assume for a fault at the end of the zone that we have 3.5 times the current coming from the strong infeed side. So we take 1, that's the red arrow, plus 3.5, that is the blue arrow, multiplied by the effective tower grounding resistance, multiplied by 1.5, and that brings us to 22 ohms. For the classic method, this break up into the parts is the same. The basic difference is we divide here the thing by 1 plus RE divided by RL. So that is the reason why we get a little bit a lower value there. And again, here you must make up your mind then finally what is now the ratio between the R setting and the X setting. Is it in this range where we want to have it? So that was the setting example. One remark I would like to add, of course, you always have a risk that you have some special type of fault which are outside your assumptions, depending on the assumed current ratio from the other side or whatever. So the question is, what is going to happen if your setting is not sufficient? And I would like to discuss one case in this context. Let's assume we have this line here protected by distance relays. We have a fault on the middle of the line. And we assume that we have a pretty strong infeed on the right side and a weaker infeed on the left side, as we had it in the simulations. That would mean, in case of the fault on the middle of the line, it would not be symmetrical. We would have more current from the right side. That's the big arrow here, and less current from the left side. What does that mean now if we apply the distance principle to that? We get here, again, depending on the setting and on the algorithms we use, we get the red arrow, and the left relay has a pretty long blue arrow because the ratio right side divided by left side of the currents is pretty high. That means the blue arrow becomes pretty long. And in this case, we assume we didn't make a sufficient setting, so we are outside the zone. That means this relay would not trip with zone 1 under these conditions. What is happening on the right side? In the same conditions, the right side, the current ratio is of course calculated the other way around. It has to take current from the left side divided by current from the right side, and that ratio is less than 1. That means for the relay on the right side, the blue arrow is much shorter, and if we have an appropriate setting here, we assume that the result is inside the first zone. And that means in this case, the left relay would not trip and the right relay would trip. So question, is that a disaster? Of course it's not good, but what's going to happen? The right relay will trip, it will open the breaker, and then the infeed from the right side has gone once the breaker is open, and that now means on the left side the blue arrow disappears, and that means the measurement is inside the zone, and then also the left relay will trip. That means in this case we do not get a complete protection failure. What we get is a sequential trip. It's not nice, but it's better, it's much better than just a zone 2 trip. And if you would apply teleprotection, it would be even better. So you see often a combination of different things helps us. With that we come to the end. Just the conclusion. We had a look at resistive faults. We saw that especially remote infeed and pre-fault power flow influence the distance measurement. The amount of influence is different for the two distance measurement we reduces, and we also saw that for the application of the RMD method, we especially reduce the influence of the pre-fault load flow, because the pre-fault load flow with the classic method brings us tilting of the blue arrow, and that can bring us a missing trip or a resistive trip, and that is avoided with the use of the RMD method. Thank you for listening.
Dear audience, if you are interested in more detailed information and practical training, please visit our training platform at Siemens Power Academy. I am confident you'll find the right resources and training there. A link to the recording and the slides will be sent to all participants. Thank you for your active participation. I look forward to meet you soon. Stay safe and take care. Goodbye.